As always, links to the source code and text version of this video in the description. We've looked at the theory behind state machines and the state pattern, and we've implemented one in code using a somewhat simplified and opinionated take on the state pattern. Now, let's look at a few options we have to expand upon that design. If you'll recall, the original design called for a hierarchy of nodes with the player delegating to a state manager for state-dependent logic, which then delegated to the active state while handling the transition between states. Additionally, all of the state code was built upon the base state class, and this method works well enough for fairly simple use cases, such as a character in a simple run-and-jump platformer for instance, but it quickly falls apart if we need to do anything more advanced. What if we want a walk and run state? They require essentially the same code, but need separate input processing methods so that the walk state transitions to the run state when the right button is pressed, and the run state transitions to the walk state when the same button is released. We don't want to maintain two sets of code that's otherwise identical to handle this single difference in code. And similarly, what if we want to add a dash state? It also handles horizontal movement, but the dash state probably shouldn't be cancelled by the player letting go of a button, unlike the walk or run states. We'll again need to make an extremely similar state to handle that difference. And lastly, and perhaps most importantly, the state manager has hard-coded references to its child states, which means we'll have to whip up a new manager for a different object if it has a different collection of states, and the state reusability becomes a bit more complicated since one enumerator is used by all states. There are two techniques that can be used to fix these issues: hierarchical state machines and dependency injection. Both of these actually already exist to a degree in the original implementation, but they were underutilized and not directly discussed to keep things simpler for the introductory video. Now that we're comfortable with a basic state machine though, let's formally discuss these techniques and refactor the state machine implementation to make better use of them. So first, let's discuss hierarchical state machines. The idea behind this type of state machine is that there's a hierarchy of states available at any time, and when a logical input is received, we move through the hierarchy from most specific to most generic until one of those states handles that input. Observant viewers may notice that this is exactly what our base state class is already doing, as it provides base functions to be called in case the child classes don't implement them. Let's take that as an example of this technique and expand on it a bit to see how we can use it to handle the previously mentioned issues of wanting to have walk, run, and dash states. Really, these are all variations on horizontal movement, so let's create a class to hold some generic movement code and subclass each individual movement state from it. Our hierarchy will then consist of base state, subclassed by move state, and then subclassed by the walk, run, and dash states. As for the code, let's first create our move state, which will handle movement for the player and apply the horizontal movement based on the output of the getMovement input function. With the exception of this new method and some extra code in the input function so we can enter the dash state while walking or running, this code is essentially the original walk state code. Now we can make walk and run states by simply inheriting from this script and adding a bit of conditional logic to handle toggling between running and walking states. As for the dash state, we can use a similar script, but since we don't want movement to be cancelled by the player, we'll simply override the input function so we can't cancel early based on player input. We'll also override the getMovement input function to always return the direction the player was facing when the state was entered. Once the desired amount of time has passed for a dash, we'll simply return back to an idle or moving state. And that's a look at hierarchical state machines. There are other ways of implementing them that can be useful, but as usual, I'm just going to stick to showing my preferred method of implementation so you don't get overwhelmed by options. You could also go even further with this concept and make a lot of micro classes to really keep things small and reusable for a large project, but that's left as an exercise for those interested. Now let's discuss dependency injection. All dependency injection means is that we're going to pass in the objects we need at runtime instead of at compile time, i.e. hard coding them, and we're actually already doing this in the player and state manager classes when we let the player pass a reference of itself to the state manager, which then passes that reference to its child states so that the states don't have to know where in the application the player lives. So let's do more of this and completely decouple the states and the state machine from the player to improve code flexibility and allow states to be more easily reused on other objects, especially now that we've seen how to easily reuse code with hierarchical states. Currently, one of the biggest couplings in the entire project is the state enumerator in base state and the dictionary lookup in the state manager. This works fine for a single object, and I certainly like it better than hard coding the path to a specific script or especially node, but it makes our code pretty inflexible since we either need a different enumerator and state machine for each object with different possible states, or one giant enumerator holding every possible state any object could need. So instead, let's have each state export variables to hold a reference to the states they can transition to. At runtime, instead of passing an enum value to the state machine representing the state we want to transition to, we'll just pass this reference directly to the state machine to handle the transition. So after removing the enumerator and changing our expected return types, base state gets stripped down a fair bit, And as an example, the idle state now looks like this. There's a bit more boilerplate code that has to be written this way, since each state will need to have its own exported node paths and calls to get node, but it gives us a lot more flexibility in where and how these states are used. And lastly, after removing the dict and changing our expected types, State Manager gets smaller as well since it no longer cares what states it houses. So now we can reuse the states and associated state machine wherever we want. The state machine no longer has any specific knowledge of the states available to it, while the states can still change their transition targets as needed. The last thing that may stand out to you is that we hold a reference to the player in each state and specifically make calls to move and slide, which is a kinematic body 2D method, and animation.play, which is an animated sprite method. I'm generally okay with this type of coupling since the player is such a unique object in most games that you're most likely going to have at least some states that have some amount of coupling to the player, but you do have options for removing this coupling and abstracting everything out further. First, hierarchical state machines can alleviate a lot of the most egregious examples of coupling. Consider, for example, removing any input reading from move state so that it only handles movement based on the inputs given to it, and instead creating a subclass, say input move state, for the player that reads keyboard or controller inputs and feeds this information to the superclass's movement code. For NPCs, an AI controller can simply feed the appropriate inputs into move state or a subclass of it. Another option is to do more dependency injection, and instead of calling direct methods on the parent object, and therefore making assumptions about its structure, pass functions to the states that they can then call when they want to do something. That way, any physics body type and any animation implementation can be used within the states. Funcrefs are the thing to look up for this since we don't have first class functions in Godot, and I've made a video about them previously if you want to know more. And that's a few more options you have when coding a state machine in Godot. To sum it up, hierarchical state machines are a great way to reduce code duplication, while using dependency injection, whether via funcrefs or exported variables or what have you, can make your states more flexible and reusable in other state machines. Until next time.